stay here longer.
What?
You can stay here longer until you cool down. Hello everyone, it's
That's cool, man.
August 30th. That's wonderful. Alright, so I try to learn a new trick today, which is to turn the skateboard by pivoting on the back foot. And I think by doing this, I was leaning really hard on the truck, and I think my truck bushing is broken. It was a little bit cracked. The bushing is a little bit cracking, so I looked online to see if it's a big issue. Turns out it's not too big an issue. That it's not uncommon that the bushing will get cracked.
I didn't know it was cracked.
Mine is cracked just today because I just found out when I took it downstairs. And I was about to tell you, but then feeding the cat came to me, and then I just realized now. So it was not too big a deal, I think, but I do think the bushing is a little bit too light. Maybe I want to make it tighter. So because I found I had this issue of with the wheel biting the skateboard because I leaned too much. So the truck now being tight kind of prevent me from finding a good balance. So maybe I'll try to tighten it a little bit, but I'll keep trying at its current setup. Because again, I'm not really looking forward to do any significant trick. Like this pivoting based on the back foot is the only thing I'm trying to progress at the moment. So the ideal is I'm practicing in the courtyard, right? And then right now I just skate from one side to the other, and I'll stop, I'll turn, and I'll skate to the other side, just back and forth, back and forth. So the ideal is I skate down, but without getting off, I will just pivot, turn around, and I'll skate down the other side. And then hopefully I'll pivot the other side, because right now I'm pivoting clockwise. I also need to learn how to pivot counterclockwise. Yeah, so both sides, I need to practice that. All right, and yesterday we didn't do it. We failed, and it turns out I was close. It was just Dijkstra all the way through, and it was first to run the Dijkstra to see if there's any path based on the unmodifiable edges. If the distance is smaller than the target, then there's no way, right? But then I didn't really figure out how to proceed. But actually the solution is quite easy. So you run that once, right? And then what you're gonna do is you go through every single edge that is -1, that's modifiable. You turn it into 1, but one by one. You turn it into 1, and you run Dijkstra again. If that reduces the distance below the target, then you know that is the critical edge. Then you just adjust it such that we can reach the target, and you set everybody else to maximum. If it cannot reduce it, right, the distance to below target, you move on to make the next modifiable edge to 1. You just keep going through until you find one that's critical, right? And then you adjust it, now we find the answer. Or if you cannot find any that's critical, then you just return saying, yeah, there's no way to make it work. So yeah, that's how it was yesterday. So compared to my previous effort about 2 years ago, I think I did make improvements by knowing it's going to be Dijkstra, and it's going to be, just trying different ways to try to get to the target. But still, it was a little bit sad that I still was not able to get it to work. All right, anyway, let's try today's. It's path with maximum probability. It feels like Dijkstra again. I would say, didn't we just do this? Are you kidding me? We just did this. We did this 4 days ago. All right, we did this 4 days ago. I will do that one more time. My. So we gotta look into the other things. Alright, we do have to look into the other things. Now, the other things, by other things, I mean we need to. Yeah, I don't even know. Is this one? Yeah, I did this one. Maybe I can try this one more time. I forgot how this one is done. Because this requires. It's not Bellman-Ford. It requires. This is still Bellman. This is Floyd-Warshall. What is this? Let's compare double value. No, it's this one. It's the Tarjan. It's the Tarjan method for finding articulation. Yeah, that's the one that I'm still not 100% sure. So what do? We just, all right, just in the spirit of doing it one more time, we'll do it one more time. We'll do it one more time. I do remember last time when we tried it, it was a little bit issue somewhere. But anyway, it's not a tough question. It's not difficult at all. This is for the 31st, right? Yeah, it's for the 31st. Ah, that was. LeetCode should set up a thing that don't repeat questions. Right, this is just set up. I say don't repeat questions. At least don't repeat questions that happen within a single week. Ah. All right, so yeah, let's see. Start and what do we want to find? This, right? So I'm gonna Dijkstra it, and we are going to start at 1, and everybody is going to be 0, and then we're gonna multiply. Yeah, so we're gonna say a map of integer list of double. Yeah, remember it's double because we have to do double. Graph new hash map for int I 0I smaller than edges. All right, edges dot length I plus int edge. That is wonderful. Wait, is Jamba playing the egg? Awesome. Dot put if absent edge 0 new array list graph dot put if absent edge 1 new array list. Okay, and then graph dot get edge 0 dot add new double. Right, and we're gonna do success probability I and edge 1, and then this one will be wait, what you doing?
Cleaning include washing dishes?
I don't think so. I don't think cleaning include washing dishes. I mean, it's 2 hours, so we're going to discuss what we're going to do. So I think we do the floors, do the bathrooms, and then see how long it's gonna take.
On the kitchen.
Yeah, the kitchen. Yeah, well, just see how long it's gonna take.
My family included washing dishes.
I don't really need washing dishes. I'm okay with washing dishes. Alright, now we're gonna do yeah, I can wash dishes, you don't have to worry about it. Queue, new priority queue. I do AB. Has to be double dot compare B0. I remember that. A0 because we want to do this is the max heap. And we have double probs new double n, right? And then say double start node equal to 1, and then q dot add new double. We'll put probability first and the node second, right? And then we say while q is not empty, double temp q dot poll. We say int current int node is, well, do an int double 1, right? And double p.
How did we come up with this idea to put the ball in the eye?
Well, I came up with this while the movers are moving stuff.
Oh, you just did it?
Yeah, I just did it 2 weeks ago. We say if let's write a boolean, private boolean. Nah, I think we can just do this. Double epsilon. Yeah, remember. Double epsilon is 10 to the, so 0.000001, right? Five zeros. 1, 2, 3. 1, 2, 3, 4, 5. No, that will be sufficient. So we say if math.abs p minus probabilities node, if it's not equal to or larger than epsilon, then we'll continue. That just means it's not equal, right? Otherwise, we're gonna say for double e of graph.get node. Oh, there's some syntax error. What happened? Here, probs. I don't know why I say should be temp. Yeah, and then we say int child int e1 double pp equal to e0, right? And then what we want to do is say if pp times p is larger than probs child. Then we say probs child equal to pp times p, and q.add new double probs child and child. Well, and then we'll keep going, and then we have to go to the end. And we return props and node. All right, let's check. I can't believe it. We just did this 2 days ago. Now I have to try to do it one more time. Yep, it's standard. Yeah, we did this problem. Was that 4 days ago? All right, I remember it's going to be e plus v log v. That is the complexity of Dijkstra. They just want to do Dijkstra, right? They just want to do Dijkstra, and oh my god, you just make the same mistake over and over and over again. That was the same mistake you made last time. I cannot believe it. You just get it wrong again. Seriously, how did you forget about this again? You just keep forgetting, right? You just keep forgetting. Look, it's the exact same mistake. It's the exact same mistake that you made last time. And it's the exact same solution that you had 4 days ago. 3 days and 23 hours ago. I think I did exactly the same. I think even the names are probably the same. Oh, I think I got a little bit smarter this time. I just swapped A and B. Okay, interesting. That's when I read about Bellman-Ford, which I decided not to do because it just takes longer. And then we just do, wait, why does it have 2? I forgot. Yeah, it's just Dijkstra. Right, just Dijkstra. All right, so we're done with this, and I think all right, we have to go back to this, to this. I mean, we need to think about it again. Right, so we try to see if any node is so I think there are 2, right? If U is a root and it at least has 2 children, and last time I was trying to understand this, I understood wrong. This is right? As your DFS through, and if a node is a root, which means its parent is empty. It doesn't have a parent. Then if you have 2, right, you just DFS the whole thing and you find out it has 2 children, then yeah, it's an articulation point. If it's not the root, then you'll have a child. Basically, if it's not a root, right, then what we're trying to say is, oh, there's a silverfish. Is that what you're looking at, Jamba? Holy crap, that's a fat silverfish. It's on the ceiling. Wow. That's one of the biggest silverfish I've ever seen. Our cat is very interested in the silverfish. All right, so the other is basically what we're trying to say is, if you're not a pair at the root, then someone, right? If someone in your subtree, right, can be connected to another node that is your ancestor, right? Then you are not the articulation point. That is what it's trying to say, right? If you're not the root of the DFS tree and it has a child, some child, such that no vertex in the subtree rooted with V has a back edge to the ancestor. You see? Right there. Yeah, so that's the second one, right? That's the second one. And this is what this low mean. I mean, this is the discovery time. So we will record the discovery time of every single node. And then we'll use low U to represent the shortest discovery time, right? The shortest discovery time. And the goal is to find the shortest discovery time.
He has so much.
No, that's okay. All right, I'll be back. All right, I'm back. Yeah, so disk is your discovery time. Low is the lowest discovery time. Right? Low is lowest discovery time. So what we want to find is if we're looking at a node and we have its subtree and we want to know what is the lowest discovery time of its subtree, right? So the subtree, which means every time we go to the subtree, or from subtree we have its child, right? Right, and let me see, visited, yeah, this is just visited, that's fine. And this is the discovery time, the current time, and this is the lowest. When you visit a node for the first time, right, this is the lowest discovery time. And then you update this. And you go through this graph. If it's not being visited, you set the parent, right? You set the parent to you, right? Your child. You set its parent. You update the children. And then you just go through everything, right? Once everybody is checked, now this is very important. This is a current node, right? So basically you're saying for you go into all your children and your children's lowest, right, their lowest discovery time. So you say your lowest discovery time should be, now this I do not understand because I don't think this is right. I would write it some other way. The lowest discovery time. Because low v, if low v is the lowest discovery time of v, which means what's the earliest time that v can be discovered? Then, or we can say low v is basically if there is an ancestor from u that can go to v, and we are recording the ancestor. Yeah, this is exactly what it's trying to do. It's setting the ancestor, right? It's setting the ancestor of v, and you're using this to get low u. U is articulate point in the following case. U is root, and it has more than one children. Makes sense. Or if u is not root and the low value of one of its child. Wait, hold on. Low value of one of its child is more than the discovery value of u. Wait, hold on. This is opposite to what I was thinking. Low v larger equal to discovery time of u. Huh? Shouldn't it be smaller? Oh no, it is larger. It is larger. That means there's no back edge. My bad. Yeah, this means there's no back edge. Right? There's no back edge. one of the child is more than. Yeah, it does make sense. It does make sense. Because if you have, if u is a root, which means we go through this and then you go through again, right? You go through again, that means you have 2, then you're already within true. But if you go through once and you don't go through the second time, because you already handled everything, the parent u is you set the parent because you keep going, and eventually you will go to something that's yeah, visit v is equal to false, so you visit it. So parent v, you point in u, and then you go to this, right? Then you set as the true, you get this, and then it's parent use parent. What if I start from u? That was my question. What if you start from u? Well, if you start from u, then u will be -1, but the low v is not going to be smaller because it will connect to somebody smaller, right? Because from that perspective, you have the v already visited. Yeah. If your child has already been visited before, and it is not the parent, not your parent, right? You have a parent, so it's some others. Then your low will be set to its low, its discovery time, right? Was set to its discovery time. So basically, your low is the earliest discovery time of some node that leading to you, right? That's what low is. It's either yourself, right? It's either yourself or a node that leads to you, right? Or a node that leads to you. And then, no matter once you're done, you'll reset your low. Now this low will become, yeah, this low doesn't really matter. You're just trying to keep updating, right? So if you set this, and then this low u will also be smaller. So basically, this low u is the earliest, right? The earliest discovery time, right, of the ancestor of the subtree, of your subtree. Earliest ancestor, right? The earliest ancestor, the earliest discovery time, the discovery time of the earliest ancestor to you. Yep. Earliest ancestor to you. And then, right, and then after you go through, then you're going to check is if low v, your child, or the earliest ancestor of your subtree, right? Because it's you are here, you have a subtree, and what you're trying to find is if the subtree has an ancestor whose discovery time is earlier than you. If it is earlier than you, then you are not an articulation point because there's a back edge. But if not, right, in this case it's not, then you are. So now the question of why we have this equal sign. Well, if it's equal sign, low v is equal to discovery u. I don't know. Equal sign basically means we have someone has the same discovery time, right? Same discovery time, and it's in a loop. Yeah, this equal sign I am not so sure. Yeah, what is this equal sign? It just means either it's you, right? It's the parent, okay? Or maybe there's another node that has the same another node that has the same. What we're trying to say is, we have a u and we have, some v, right? Oh, they look exactly the same. We have a u, we have a some v, and then this v has a back edge. Now, if this back edge goes to some p, which has a lower, right, has a lower discovery time, then yeah, u is not an articulation point. But now the situation is different. Now the situation is we have some p here, which has the same discovery time as u. So we have it is a back edge, but p is not an ancestor of u. So they probably go up, something, maybe up with, maybe like that. Yes, if that is the case, right, and p is not an ancestor, I mean, even we can put a link here, it's okay. Now, if we put a link, that is not okay, because if we put a link, p can be an ancestor of u, or u can be an ancestor of p, right? Then neither is, right, you remove it, neither is the, yes, because we are doing the DFS tree, so they're always going to be who gets discovered first. So if you have a link between these two nodes, one of them will become the ancestor of the other, so we will never have the equal sign. The equal sign happens if they do not have anything linked. So no matter how, like if we go from, in fact, in this case, actually I don't know, in this case, u is still going to be the ancestor of p, right? Yeah, u is still going to be considered as a, because if I start from here, I go this, right? And for here, for this u, this is the subtree, right? And it's subtree, oh yeah, in this case, that's actually different, because in this case, eventually I go back here. So everybody is going to get, all the low is going to be this one. So your low v is going to be smaller. So yeah, no one. Yeah, no one is critical. It will be critical if there's no edge. Actually, I don't know. I don't know like what type of condition it will be so that it will have equal sign. But just conceptually, if it's equal, right? If it's equal, then that just means your subtree. Yeah, we don't care. You have your subtree, right? Has a back edge to some node which is at the same level as you, so it's not a back edge. That just means you are still a critical, an articulation node. Okay, I think I can write this. I can write this. So now the question becomes, because we need to use this to solve this problem, right? So we need to find the so are you also just removing one? Because here we just remove. Yeah, I'll get all the ones. We set to 0. We get it. Get this region. Yeah, that's what we're trying to do here. But now we are trying to find its articulation point. So are we doing the same? Just remove one. Try to find the articulation point. If there exists, then we're good. If not, then we're bad. Is that how we're trying to do? Tarjan? If there is 0 or more than one island, that is true. Return 0. Okay, what are we trying to do? To disconnect the grid. This is just the edge case. This is land cells, which is increment the land cells count. If the cell has not been visited, we do this increment island count. If we have 0 island, you return 0. If you more than 1 island, you return 0. That is true. If you only have 1 island cell, you return 1. If there is an articulation point, you return 1. So you are going through this. If you have an island, you try to find it. If you have no, then you call this to find articulation points exist. So every time you encounter, you go for it. Encounter, you go for it. Yeah, I don't understand this part. You will loop through each cell. If the cell is 1, which means it's a land, you increment the land cell count. And if the cell has not been visited before, you will call this on ij. Basically, you do a DFS on starting from here, right? To find if articulation point exists. And at this time, the graph is not fulfilled yet. Right, it's not fulfilled yet. And then you just say, yeah, it's not fulfilled, and then we try to see if there's articulation point. And if there is, are you saying that if there is, then why can't we just do it the same way? Like we just remove one, which is 1 by 1, right? We remove 1. We see if there's articulation point. If there is, then we're good. If there is not, then we are bad. I don't understand why you have to go the other way around. Yeah, I don't quite understand. I do not quite understand. Yeah, I don't understand why you can just go 1 by 1. Yeah, this part is the part I don't understand. And what does this one do? Land cells. Okay. Has articulation point. An articulation point exists. Like it's throughout the way. Right, because if it does not exist, hold on. as you go through, you're running this articulation point. Huh? Yeah, you run the articulation point kind of consecutively, right? Kind of consecutively. And the previous running will be, they're recorded. The previous runnings are recorded. Because if you look at this, discovery time is this. This is the like a global, right? You get discovery time, you get this, you get the children. So you're starting from whatever you are, and you try to run. And then is valid cell. Okay, is valid cell. Is valid cell doesn't check if you run it before. So you start from some stuff. Oh, my bad. My bad. This is just say if it has not go before, and then this one will run the entire thing. Oh yeah, my bad. Yeah, this will run the entire thing. Okay. So this will run the entire thing, try to find if we have an articulation point. And if it already has an articulation point. It makes sense. All right. Okay, I know. Man, it took so long for me to understand. Yes. Basically, yeah, we when we hit an island, we run the Tarjan algorithm to find if an articulation point exists. If it exists, we basically can turn off right there. If it exists, we just remove that, and then we become. The answer is 1. If it does not exist, we just keep going. Okay, I got it. Yeah. All right. So now the task is to write Tarjan from scratch. God, Lord. Yep, definitely not using Java to do this, and I don't want to do it today. Okay, let me go through Tarjan one more time. So using Tarjan to find articulation point, we need to basically create a DFS tree. And as we go through a DFS tree, we will have discovery time assigned to every single node. And a node is an articulation point if it is the root of your DFS tree and it has 2 children. That basically means it's there are 2 separate subtrees that's connected to this root, and those 2 subtrees don't have a connection, right? Because if they do, then you will not have 2 children, right? So that's one. The second situation is you are not a root, okay? So you're somewhere inside, and all of your children, or you can say your subtree, every node in a subtree does not have a ancestor whose discovery time is smaller than you. Yeah, and it will use low as a way to keep track of the earliest discovery time of your ancestor. Yep, that's that. Okay. If tomorrow we got we got it done fast, I think I can do this. All right, we'll stop right here and I see you guys tomorrow. Adios.